In lesson 3.3, there are two main objectives, and one is to apply the properties of logarithms. The second one is to apply the change of base formula. So far in this unit, we've looked at exponential curves, either growth or decay. We've also looked at a couple of different exponential growth and decay models, whether it's continuous growth or whether it's periodic growth. And we had two different equations for that. In the next investigation, in the next lesson in 3.2, we looked at logarithm curves, and we were sketching graphs of logarithms, and we were also evaluating some logarithms. In this one, we're going to learn three properties of logarithms that'll help us evaluate and solve logarithmic equations. And the second thing is, like we mentioned, we're going to use a change of base formula to help us evaluate logs of bases other than base 10 and base e. A big thrust of this is being able to understand the logarithm properties. There are three main properties that we're going to discuss here and we're going to prove. I want to come back to what we've learned in lesson 3.2, and that is the definition of a logarithm. By definition, a logarithm is defined this way. The log of any base of an antilog. Okay, give me just a second. I have to orient the board since it got pushed around again. Okay, as I was trying to point out, by definition, the log of any base of an antilog, which is your number, will give you the exponent. So really, logs are really always connected to exponents. Logs are designed to find the exponent. And I just rewrote it in the exponential format. Remember, we practiced on changing format. So this is another way of writing in the exponential format. And sometimes it gives us better meaning this way. But we can always keep the base the same. Now we would take the base to the exponent. So the exponent becomes our new, our exponent on the base. And that has to equal the antilog. Or typically what we look at is this expression here. Log base b of a is x if and only if b to the x equals a. So as long as we can take x and raise it b to the power of x to get a, that's how our logarithm is defined. So we've got that definition in mind, and we learned that in lesson 3.2. Now we're going to put that together with some properties of logarithms as well. Because logarithms and exponents are closely related, they're inverses of each other, some of these properties have a lot of carryover value, so there's a lot of correlation between the things that you know about exponent properties and logarithm properties. So I'm going to begin this discussion by looking at our exponential properties that we've learned. And we reviewed those in chapter 0, I believe. But exponent properties, there are three main rules of exponent properties, and I threw in the fourth one in there just to review it. But the first one is the product property. And the product property basically says when you multiply like bases, you can add their exponents to get your result. So if we have b to the x times b to the y, as long as those bases are the same number, then we can take the exponents and just add them together to get our new expression. The second rule is the quotient property. And the quotient property is used when we divide like bases, and we know that we subtract the exponents. So it's the same base in both of those expressions. If you divide like bases, you take the exponents and you subtract them. And the third one that we're really going to focus on is the power property. That says whenever you take a power and you raise it to another power, you multiply the exponent. So if it's b raised to the x raised to the power of y, since it's a power raised to a power, you multiply your exponents to get your result. And then the fourth one I thought we may as well review, because there is a fourth rule in here about exponents that we sometimes stumble across, and that is anything raised to a negative exponent, you reciprocate and raise to the positive power. So I just wrote this in here: reciprocate the base and raise the power to a positive power. So if it's b to the negative 1, we reciprocate the base. So since it's b over 1, we reciprocate, it's 1 over b, and now we raise it to the positive power of x. So those four rules, and in particular, I'm going to look at these three rules. Somebody took their clumsy pills today. And we got these three that have high correlations to the three logarithm properties that we're studying, which are these, the same things: the product property, the quotient property, and we also have the power property. And that got off just a little bit, and I'm going to go back and fix that so it isn't pointing to the wrong thing. There, I got that corrected. I wanted the arrow to point to the correct ones. I wanted to draw your attention to the correlation between these properties. And here's the thing that always helps me, and then I'm going to go into some derivation of these properties. Since I know that logarithms are basically exponents, and I'm coming back to this idea, logarithms always give you an exponent, and logarithms are similar to an exponent, then the log properties and the exponent properties have to be closely related. So if you look at the property of exponents, the product property, and you compare it to the product property of logarithms. Since logarithms are exponents, if you take the log of a product, then what we want to do is we want to equal the sum of the logs. If logs are really exponents, then the only time that we add exponents is when we're multiplying the bases together. So to me, this has some carryover because I see multiplication. If I see multiplication of a logarithm, I'm going to correlate it back to what do we do when we multiply like bases on exponent rules? Well, we add those exponents. And since a logarithm represents an exponent, here's our addition of two exponents. The other one that's highly correlated is the quotient property to the quotient property of exponents. So the quotient property of exponents, say if you divide like bases, you subtract exponents. Well, we're going to look at a quotient property of logarithms. And it basically says, I'm going to take the log of base b of a quotient. Here's the quotient of x over y. If we take the log of a quotient, since logarithms are exponents, the only time that we subtract exponents is when we are dividing our like bases. And that's the corollary I'm coming back to over here. There's a high correlation between, if we see division in a logarithm, we got to think of it, what's the rule in our exponent rules? If you divide like bases, you subtract exponents, so therefore, since logarithms are exponents, if you see a division problem in logs, the logs are simply going to be an extension of the exponent rules, and you subtract those exponents. And finally, the last one is the power property. The power property also correlates over here with a logarithm property. It says the log of the power is the power times the log. So really, we're taking a power times the log, and a log is a power. So our power property over here on the exponents is, if we have a power raised to a power, we multiply exponents. The only time we multiply exponents when it's a power raised to a power. Well, since logarithms are exponents, what we're doing is we're taking an exponent raised to a power. So that means we can multiply the exponents together. P is an exponent, and log of base b of x is an exponent, so we're going to use our correlation, how it correlates back to, if we see power to power, a logarithm is an exponent raised to another power, then we should be able to multiply those two things together. So one of the things I want to stress here is trying to put these in words. If you put them in words, a lot of times you're much better able to apply them. So I've got these things written out here, so I'm going to focus on this product property for a moment. It says the log of a product is the sum of the logs. The log of a product, I'm multiplying there, is equal to the sum of the logs. Now that is hard for some people to do because they think of a distributive property. Logarithms are not distributive. Do not do log of base b of x and then take it times the log of base b of y. That is not accurate. That is incorrect. So I'm just throwing that disclaimer out there right now. What you have to get used to is thinking of logarithms as exponents. I see multiplication, therefore I have to add. The second one, the quotient property. The log of a quotient is the difference of the logs. So we're seeing the log of a quotient. When we see quotient, anytime it deals with exponents, we should be thinking of subtracting them, just as the correlation back there. So again, try to verbalize. This quotient rule says the log of a quotient is the difference of the logs. The product rule says the log of a product is the sum of the logs. And finally, in words, this power property, it says the log of a power is the power times the log. When we see multiplication of a number times a log, we're thinking of multiplying exponents together. The only time that happens is when an exponent was raised to another power. And that's coming back to this rule here. So we got the three that are highly correlated to each other. And that's what we're going to be practicing here, using those properties. They try to prove these, and they also prove it in your textbook. They prove one of the three. We're going to quickly run through each of these, and we're going to prove the product property. Now, in a traditional sense, here's what they typically will do to let these, or to prove these. And the first thing they say is, well, let's let by defining that x is equal to b to the m, and the value of y is equal to b to the n. So this is going to be a rule of substitution, but the first thing is to say, well, let's let x and y represent an exponent b to the m and b to the n. If that is true, then by definition of logarithm that we studied up above in lesson 3.2, I can rewrite this as the log of base b of x equals m. This is the format change that we got used to doing in lesson 2, and also what I reviewed with you at the very beginning of this. And the other thing we can do is we can rewrite y as log base b of y equals n. So those are equivalencies between exponential format and log format. So then they traditionally do this. So okay, let's start with this log of base b of x times y. I want to prove this equal to the log of base b plus the log of base b of y. Well, the first thing I'm going to do is going to make a substitution. X and y, we now have replacement values for them, and I'm going to put log of base b of x, well, x is equal to b to the m times y, and replace y with what y is equivalent to, and we said y is equivalent to b to the n. So this is simply by substitution property of equality. So I'm replacing the x with what x is equal to up here, and replacing the y with what y is equal to up here. Now what we have is a log of base b of b to the m times b to the n. Well, b to the m times b to the n, we can apply one of our exponent rules. If you multiply like bases, you can rewrite this as b to the m plus n. So this is our power or product rule of exponents. So I'll just go product of expo. Product rule. At this stage, what we can do is we can use this inverse property that we studied in lesson 3.2. The log of base b of b to the m plus n, since the log of base b is then followed by an exponential of base b, these are inverses of each other, and they cancel, and you just get m plus n. So they call this an inverse property of logs in lesson 3.2. But now we're going to come back and say, well, what did m represent to begin with? M was a representation of log of base b of x. N is a representation of log base b of y, so plus log base b of y. So therefore, the log of a product of x times y has to be equal to the sum of the logs, the log of base b, the sum of the logs of base b of x and log base b of y. That is a very traditional proof of that property, and that's one of the three that I'd like to run through with you. Once you have that concept down, then the next one is pretty similar to it. So I'm going to clear that off. I'm going to move over the quotient property, and this is a very similar strategy to this. In this, if you're going to prove it, then the first thing you're going to do is just like I started in the other proof, we're going to start off with, well, let's let x equal b to the m, and we'll let y equal b to the n. Then we can rewrite these using a logarithm format. An equivalent logarithm format is log of base b of x equals m. This one has to be log of base b of y equals n. Remember, logs equal to your exponents. So what we're trying to prove then is that the log of base b of x divided by y, which is a quotient, is equivalent to the log of base b of x minus the log base b of y. Well, first thing I'm going to do is I'm going to make this substitution again like we did last time, which means I'm going to take out x and I'm going to replace it with an equivalency, which was x was equal to b to the m divided by, and I'm going to take out the equivalency, what was y equal to, and that was b to the m. And the next step, and I guess I could put substitution, property of equality on that again. So substitution. The next thing we're going to do is we're going to use a log or an exponent property. Whenever we have the same bases divided, what we do is we use our quotient rule. Our quotient rule says if we divide like bases, we subtract exponents. So I could rewrite this as b to the m minus n. So this is the quotient rule of exponents. So quotient rule of exponents, just to kind of get your mind wrapped around that. Then the next thing that we're going to do is we're going to apply that inverse property that we did in the last proof, which means the log of base b of b raised to the m minus n, that's that inverse property of logarithms. The log of base b followed immediately by an exponential of base b, cancel, so it's m minus n. That's the inverse property of log. And then we're going to come back and substitute in the values of m and n. So m represented the log base b of x, and n represented the log base b of n, which is what we were setting out to prove. We wanted to prove that the log of a quotient, which is here, is equal to the difference of the logs. All right, there's one other proof that's remaining. Let's see if I can pull that one up, and that's the power property. Okay, so I'm going to leave that here. So in the first stage of this, very similar to what we've looked at before, we're going to let x equal b to the whatever you want. I guess n is what we've been using before, or m. It doesn't make any difference. I think I've had m, so I'll use m again. So that means we can rewrite this using an equivalent logarithm statement as log a base b of x equals m. But we want to prove that the log a base b of x raised to the p is equivalent to p times the log of base b. So the first thing I'm going to do is I'm going to make the substitution. What is x equivalent to? Well, x is equivalent to, based on our let statement, x is equal to b to the m, and then we want to take that and raise it to the power of p. Now, according to our exponent rules, whenever we take a power raised to a power, such as we have here, it's the same thing as log a base b of b to the m times p. Then we can use our inverse of logarithm property. So the log of base b followed immediately by an exponential of base b. These are inverses, and they simplify or reduce, and we've got m times p. So what does m represent? I'm going to go back up, and m represented log a base b of x. We're supposed to take that times p. And then we can use a commutative property so it looks just like they have it. P times the log of base b times x. And the parentheses aren't really needed. I just did it for clarity. I thought it kind of clears what we were doing up. And there's our properties. Now that is three formal proofs or derivations of these log properties. In the context of all things, I'd like you to have a good concept of what we were doing here and how these properties were related and used. But I thought that would be good to show you that right up front. We're really focused on these three properties. The log of a product is the sum of the logs. The log of a quotient is the difference of the logs. And the log of a power is the power times the log.